In all of scientific history, Michio Kaku once said, the greatest shock isn't discovering the unknown, it's realizing the unknown has been watching us all along. And tonight, that very idea takes on new weight. The interstellar visitor known as 3I Atlas has reappeared after vanishing behind the sun. And what it's doing now is forcing scientists to question everything they thought they knew about how the universe behaves. Did this cosmic traveler simply survive its fiery passage, or did it change? What happened during those hidden weeks when no telescope could see it? And why does its return defy almost every rule of space physics we've trusted for centuries? Because if what astronomers are witnessing is real, the implications go far beyond astronomy. They reach into the heart of one unsettling question, one that Michio Kaku has warned we would face someday. What if we were never truly alone in the first place? For weeks, space itself seemed to swallow the visitor whole. 3I Atlas had vanished behind the sun's blinding glare, slipping beyond the reach of every telescope on Earth. That silence, what most assumed was the end of its story, became the most anticipated moment in modern astronomy. Scientists waited as if for the return of a lost probe on an impossible mission. And then, it came back. Emerging from the solar shadows, the object shone brighter than before, as if something on its surface had awakened. Instead of a body weakened by radiation, it reappeared active, pulsing with fresh emissions. For astronomers trained to expect predictability, this was a cosmic alarm bell. Images from southern hemisphere observatories revealed a coma, a cloud of gas and dust, behaving unlike any ever recorded. Density waves seemed to ripple through it, rhythmic and structured, as if the nucleus were responding to an internal pulse. Each oscillation of light hinted at movement, not random, but deliberate. The anomaly drew the attention of planetary defense networks. The Near-Earth Object Center reclassified 3I Atlas as an active anomaly, a label reserved for bodies that defy simple gravitational behavior. In practice, it meant one thing: nature wasn't fully in control anymore. Across the globe, observatories scrambled. The Hubble, the Webb, and ESA's optical arrays synchronized their tracking to capture every spectrum, every flicker. The world's best instruments were suddenly united by the same question. Had we just witnessed a comet being reborn, or something else awakening in the dark? Among researchers, emotions split between awe and unease. Every return of the invisible is a test of humility, Michio Kaku once said during a lecture on interstellar phenomena. His words echoed through control rooms. In front of the unknown, danger isn't our enemy, ignorance is. Then came the first velocity readings. 3I Atlas wasn't just back, it was slower. Somehow, while hidden behind the sun, it had changed its speed. And that single observation raised the most haunting question yet. What exactly happened in the light we could not see? Michio Kaku has often said that the greatest challenge in modern physics isn't confronting the impossible, it's confronting the unexpected. In an interview with the BBC, he remarked, "The frontier of knowledge isn't a wall, it's a mirror. What we see reflected there is ourselves, trying to understand our own astonishment. That mirror now hangs above 3I Atlas." When the data began breaking classical equations, Kaku's words resurfaced across the scientific world. Part warning, part inspiration. For decades, he's argued that advanced civilizations might manipulate stellar energy in ways that would look unnatural to us. 3I Atlas suddenly turned that theory from speculation into observation. But Kaku never claimed the object was artificial. His point is subtler, that the very concept of natural depends on how much we know. When something behaves beyond prediction, the right response isn't fear, it's the courage to rewrite our model of reality. That mindset is what separates panic from progress. Inside observatories, that shift in thinking is underway. Physicists trained to find order now face something that seems purposefully disordered, almost playful in its defiance of pattern. 3i Atlas isn't just breaking physics, it's testing human psychology under uncertainty. The universe, it seems, is running an experiment on us. And that experiment has a clear effect. It fuels imagination. Kaku often reminds students that curiosity is the most powerful energy in the cosmos. Inspired by that idea, astronomers began proposing new models, unknown materials, thermal conduits, even internal structures that redirect sunlight with impossible precision. What began as a technical anomaly has become a philosophical pivot. What does intelligence even mean if it can be embedded in cosmic architecture? Could 3i Atlas be a technological fossil, a relic of engineering lost between the stars? The questions now matter more than the answers. That's why Kaku's quote feels less like commentary and more like instruction. Don't fear the unknown, that's where knowledge lives. Around the planet, instruments are aligned, data streams analyzed, eyes fixed on a single traveler. Somewhere beyond the sun, that mirror Kaku spoke of is reflecting humanity's curiosity right back at us. It all began with a dot, a flicker of light detected by the Atlas Sky Survey telescope in the southern hemisphere. At first glance, it looked like just another icy wanderer, a comet drifting in from the edge of our system. But within minutes, orbital calculations told a different story. The path didn't close into an ellipse. 3i Atlas wasn't from here. To call something interstellar isn't poetic, it's revolutionary. It means the object was born under another star's gravity, not our sun's. A true outsider. Since 2017, humanity had found only two such visitors, Oumuamua and Borisov. Now a third had arrived, and this one carried anomalies that made both of its predecessors seem ordinary. Its velocity exceeded 130,000 miles per hour, and its trajectory intersected the solar system's orbital plane with uncanny precision. Random debris shouldn't move this way. The orbit looked deliberate, smooth, clean, coherent, as if steered by invisible mathematics. Nature is rarely that tidy. As word spread, observatories worldwide rushed to collect every photon they could. Ground-based telescopes, spaceborne cameras, and radar arrays scrambled to measure its density and reflectivity. The results were baffling. The surface reflected light like polished metal or crystalline ice, neither fully cometary nor fully mineral. Excitement quickly turned to unease. This was a once-in-a-century opportunity to study something from another star. But the alignment was too perfect. The newcomer would skim close to several planetary orbits, crossing zones densely monitored by space agencies. For something supposedly random, it was threading a cosmic needle. Forums lit up with theories. Could such precision really be coincidence? Statistically, maybe, but cosmically, it strained belief. Some researchers warned that science doesn't forbid coincidences, it just demands that they make sense. This one didn't. 3i Atlas seemed to choose its path. Not with intention we could prove, but with precision we couldn't ignore. Each new calculation deepened the mystery, suggesting a logic still beyond us. Its arrival was more than an astronomical event. It was a quiet reminder that the unknown knows exactly where to find us. The first confirmed anomaly in 3i Atlas wasn't chemical or visual. It was geometric. When astronomers plotted its path across the solar system, they discovered something almost impossible. The object traveled within less than 5 degrees of the ecliptic plane, the thin disk where all our planets orbit. For an interstellar traveler, that level of alignment is astronomically rare. The probability was microscopic, less than 2 in 1,000. Statistically, it was like throwing a dart blindfolded and hitting the bullseye of a target you didn't know existed. Such precision unsettled scientists not because it implied intent, but because nature seldom produces symmetry this perfect across unrelated systems. The orbit stability deepened the puzzle. Even after passing near the gravitational fields of Mars and Venus, 3I Atlas held its trajectory almost unchanged, as if it had corrected itself mid-flight. No debris, no wobble, just an elegant line of motion across the void. To skeptics, it was cosmic luck. To others, a hint that something non-random was at work. Nature is beautiful in its chaos, but when chaos starts behaving like choreography, curiosity takes on a sharper edge. The universe doesn't write in straight lines unless it means to. Independent labs rechecked the data from observatories in Chile, Japan, and Europe. All came back identical. No calibration errors, no gravitational explanation that fit. If 3I Atlas were a conventional comet, it should have shown measurable perturbations while crossing Mars' orbit. Instead, it moved as though the planet wasn't even there. As Michio Kaku once observed, the cosmos delights in improbable events, but never without a lesson. Perhaps this was one of those lessons, that order and randomness are not opposites, but partners in a game we still don't know how to play. And just as the math settled into its eerie perfection, a new shock appeared. The tail, that familiar signature of every comet, began to twist. Instead of streaming away from the sun, it turned back toward it. The universe had just flipped one of its own rules upside down. Every comet obeys the same elegant law. As sunlight heats its surface, frozen gases vaporize and stream outward, forming a tail that always points away from the sun. It's a simple dance. Pushes, the comet yields. But 3I Atlas broke that choreography. Its primary jet was facing toward the sun. At first, astronomers blamed perspective. Maybe Earth's viewing angle distorted the direction. Yet telescopes separated by thousands of miles, 3 continents, reported the same thing. The material wasn't being blown away from the sun. It was flowing directly toward it. A solar contraflow, something that shouldn't exist. Spectral data deepened the mystery. The emissions showed high levels of metallic particles and carbon dioxide. An odd combination. But what baffled scientists most was the strength of the jet. It resisted solar pressure, almost as if powered from within. The outflow wasn't passive, it was active, structured, and self-sustaining. Researchers proposed natural explanations. Maybe hidden cavities were redirecting gas through complex geometry, creating the illusion of a reverse jet. But the math didn't work. The pressure required to maintain that pattern demanded an internal energy source, or an architecture never before seen in a comet. NASA redirected the James Webb Space Telescope for a closer look. Its instruments confirmed a carbon dioxide to water ratio more than 80-1, the highest ever recorded. That alone changed the physics of cometary activity. Yet even with this extreme composition, the jet's direction made no sense. It was as if the object were deliberately feeding the sun. When nature breaks its own rules, Michio Kaku once said, it's trying to teach us new ones. Perhaps 3I Atlas is doing exactly that, showing us the limits of what we think we understand about matter and energy in the cold of interstellar space. Or, as some quietly wonder, it might be demonstrating design disguised as nature. The inverted jet marked a turning point. From that moment on, 3I Atlas stopped being merely a comet. It became a question, one that seemed to be answering itself through impossible physics. If sunlight couldn't push it back, then what was really driving it forward? When NASA's James Webb Telescope locked on to 3I Atlas, astronomers expected a familiar spectrum: traces of water, dust, and a few organic compounds. What they found instead defied classification. The readings showed enormous concentrations of carbon dioxide, cyanide gas, and shockingly, vaporized nickel, a metallic signature almost never seen in nature. Carbon dioxide dominated the mix, outnumbering water vapor by a factor of 80. That ratio made no thermal sense. At those distances from the sun, the ice shouldn't have vaporized so efficiently. It was as if something within the object were controlling the gas flow, channeling it through vents with deliberate precision. Then came the truly disturbing data from the European Southern Observatory. The nickel-to-iron ratio in 3I Atlas matched the balance found in industrial alloys, materials produced by engineering, not geology. The resemblance was so precise that one researcher privately compared it to finding stainless steel inside an iceberg. Theories emerged fast. Perhaps the sun's heat triggered exotic chemical reactions, releasing trapped metals from ancient collisions. But the math refused to cooperate. Under solar temperatures, iron should dominate, not nickel. Nature doesn't invert those ratios on its own. Something in that chemistry was wrong, or perfectly right, depending on how you looked at it. Some scientists urged restraint. Unknown reactions can mimic artificiality. Others leaned into the curiosity. After all, the universe is old enough to preserve the ruins of its own experiments. Michio Kaku once noted, "The cosmos has had billions of years to build and to forget." Maybe 3I Atlas was one of those forgotten relics, a frozen blueprint of something once built and left to drift. Between caution and wonder, consensus emerged. Investigate, but don't assume. Agencies worldwide coordinated a unified spectroscopic campaign, comparing data from every major observatory. The goal? To determine whether 3I Atlas followed the chemistry of nature or the fingerprint of technology. And as the numbers poured in, another anomaly surfaced. The object was too bright for its estimated mass, reflecting far more sunlight than its size allowed. Whatever was shining out there wasn't heavy enough to account for its glow, which meant the next mystery wouldn't be about composition, but gravity itself. In space, light and mass are supposed to dance in harmony. The brighter an object shines, the heavier it usually is. But with 3I Atlas, that relationship broke down. As it passed near Mars, astronomers measured an almost non-existent gravitational influence. It glowed like a giant, yet pulled like a feather. Something didn't add up. The numbers were unsettling. Based on its brightness, the object should weigh tens of billions of tons. Yet orbital tracking showed barely a trace of mass. It was as if a massive shell were masquerading as a solid core, an enormous form with the inertia of dust. Scientists gave it a new name: phantom mass. Astrophysicists compared it to a soap bubble reflecting sunlight, luminous, fragile, yet nearly weightless. But this bubble was kilometers wide and surviving conditions that should have torn it apart. Simulations suggested only one plausible scenario. The interior had to be hollow, an empty chamber enclosed by a resilient outer layer. That possibility opened a floodgate of speculation. What if 3I Atlas wasn't a solid rock, but a shell, a casing built for endurance rather than weight? Some engineers pointed out that such structures resemble theoretical designs for interstellar probes, lightweight, thermally resistant, and capable of redirecting radiation for propulsion. Skeptics countered that natural fragmentation could reduce apparent density without invoking technology, but the object's rotation didn't fit that narrative. It spun too slowly for a loose aggregate and too steadily for debris. The math described something cohesive, a single, unified body behaving like a designed construct. Michio Kaku once said, "The difference between a rock and a machine is sometimes just the consistency of its motion." That thought echoed across control rooms. Because this rock moved with the steadiness of engineering, not accident. It didn't tumble, it cruised. With a mass too light, a brightness too high, and a trajectory too clean, 3I Atlas became more than a comet. It became a gravitational paradox, a riddle that science could measure but not yet define. And as the questions grew louder, the flow of new data began to slow. Silence, once again, was filling the gap where certainty should be. After 3I Atlas reappeared, the world expected an avalanche of data. Telescopes had been collecting readings for weeks. But instead, everything slowed. Updates that usually arrive in real time began to lag. Reports disappeared. Observation windows were postponed under a familiar phrase, awaiting technical review. Officially, agencies blamed calibration issues and overloaded data pipelines. Unofficially, scientists admitted something deeper. The numbers didn't make sense. Instruments disagreed. Models broke. The object wasn't behaving according to any known physics. The delay, they said privately, was less about secrecy and more about confusion. It wasn't the first time this had happened. Oumuamua and Borisov both caused similar quiet periods after unexpected findings. But this silence felt coordinated, or at least cautious. With more than 20 spacecraft and dozens of observatories tracking 3I Atlas, it was hard to believe they were all reprocessing at once. Michio Kaku has long warned that institutions grow silent when data threatens to rewrite their frameworks. When the facts don't fit, science pauses, he once said. That's not conspiracy, it's self-preservation. His insight suddenly felt prophetic. Caution, not concealment, seemed to rule the day. Meanwhile, independent astronomers filled the void. Observers in Germany, Chile, and Australia began posting images online, raw, unfiltered, showing strange surges of brightness that official charts ignored. None of them claimed revelation, but all agreed on one thing: the object was active. Something inside it was changing. Science forums became improvised control rooms. Amateur and professional data collided, revealing trends that shouldn't exist. Subtle pulses in luminosity, periodic as clockwork. To some, it looked like rotation. To others, like a signal. The lack of answers only amplified the noise, and that's the paradox. In the space between fact and explanation, silence becomes communication. Institutions withheld information not out of secrecy, but out of fear of misinterpretation. Yet silence breeds speculation, and speculation, in turn, becomes the fuel of curiosity. The world was listening closely to the silence itself. As astronomers struggled to make sense of the silence, one alignment caught their attention. 3I Atlas disappeared exactly when it reached maximum velocity near the Sun, the most energetic point of its orbit. For engineers, that instant has a name: the Oberth point, the ideal moment for a spacecraft to change course. The timing felt too perfect to ignore. The Oberth effect is a real maneuver used by human-made probes. By firing thrusters at their highest orbital speed, they gain exponential energy from gravity's pull. It's the most efficient way to accelerate or slow down using minimal fuel. 3I Atlas passed through that window at the precise time no one could see it. For nearly 3 weeks it was invisible, hidden behind the sun's overwhelming light. That meant no telescopes, no sensors, no data. If any kind of adjustment occurred, it would have happened there, unseen. The question was unavoidable. Did this object use the sun, and if so, how? Calculations showed that at its closest approach, 3I Atlas absorbed over 30 gigawatts of solar energy, equivalent to 1/3 of all nuclear power generated on Earth. If even a fraction of that energy were redirected or stored, it could alter its velocity dramatically. Physics doesn't forbid it. Nature simply doesn't do it, not on its own. Some dismissed it as coincidence, others refused to rule out intent. Michio Kaku has often said, The sun is the ultimate laboratory. If something can harness it, that something is no longer random. His words resonated as the orbital charts came in. The object's path had shifted, subtly but undeniably. Post-perihelion data revealed a tiny yet measurable deceleration, as though 3I Atlas had tapped the sun's energy not to speed up but to slow down. To engineers, that's exactly what a controlled entry maneuver would look like. To astronomers, it was another statistical impossibility stacked on top of dozens before it. At that point, the mystery was no longer just astronomical. It had crossed into the realm of mechanics, of navigation. If 3I Atlas truly changed its own trajectory while hidden behind the sun, then we may not be watching a comet at all, but something following a flight plan. To understand what might have happened to 3I Atlas behind the sun, we need to revisit one of spaceflight's most elegant principles, the Oberth effect. Proposed in the early 1900s, it explains how a spacecraft can gain massive efficiency by firing its engines at the point of highest velocity near a gravitational body. In other words, the faster you go, the more energy each burst of thrust gives you. Humanity has used this trick before. Voyager, Cassini, and the Parker Solar Probe all relied on Oberth maneuvers to slingshot through the solar system, but these are carefully planned operations, the result of calculations and control. A comet, by contrast, doesn't plan, it simply falls. And yet 3I Atlas seemed to act as if it had. Its disappearance coincided perfectly with the time an Oberth maneuver would occur. For nearly 3 weeks it was invisible, and when it returned, its velocity had dropped slightly. To the untrained eye, a minor detail. To physicists, a potential signature of deliberate braking. If 3I Atlas was slowing down, it was choosing to stay. At perihelion, solar radiation bathed its 5-kilometer body with over 30 gigawatts of energy, the kind of power engineers dream about. That's roughly a third of the nuclear output of the United States. Enough to vaporize, propel, or even charge something. The sun provided the energy. The question is who or what used it? Michio Kaku has long speculated that an advanced civilization could manipulate solar energy the way sailors once used wind, not to fight nature, but to cooperate with it. For those who harness the stars, he said, gravity is not an obstacle, it's a steering wheel. If 3I Atlas truly performed such a feat, we may have just witnessed celestial navigation at work. To test that idea, astronomers compared pre- and post-perihelion trajectories. Even the smallest shift would transform speculation into data. The results were subtle, but consistent. A slight course correction, impossible to attribute to solar drag alone. It was as though the comet had executed a move. What happened behind the sun will never be captured on camera, but it's written in mathematics, and the numbers whisper something extraordinary. 3I Atlas didn't just survive the sun or think it may have used it. If true, this wouldn't just be another anomaly. It would be the first evidence that interstellar travel and celestial mechanics might already share the same language. As telescopes on Earth strained to track 3I Atlas, new eyes turned toward it, robotic ones scattered across the solar system. The European Space Agency redirected instruments from its JUICE mission, originally bound for Jupiter, to collect data on the interstellar visitor. Meanwhile, orbiters circling Mars, the Trace Gas Orbiter and Mars Express, caught faint glimpses of the traveler as it crossed their field of view. The images were faint but revealing. The coma surrounding 3I Atlas didn't flicker randomly, it pulsed. Its brightness rose and fell in perfect rhythm, as if the object were breathing light. Astronomers ran simulations trying to match natural processes to this heartbeat pattern. None fit. No other comet had ever behaved this way. More surprises followed. When 3I Atlas passed near Mars, its gravitational pull was practically non-existent. Instruments sensitive enough to detect tiny orbital shifts saw nothing. For a body several miles wide, that was impossible. The only conclusion left was the most counterintuitive. It was too light for its size, maybe even hollow. That shell hypothesis returned with renewed force. Could it be a thin casing designed to endure heat while staying buoyant? Some engineers compared it to theoretical light sail concepts, vast reflective structures built to ride radiation rather than resist it. A relic, perhaps, from a civilization that understood how to let the stars do the work. Kaku once remarked that the best technology is indistinguishable from a miracle of nature until you learn how it's built. His words felt prophetic as data from multiple probes began to converge. The brightness fluctuations weren't noise, they followed ratios that looked mathematical. Patterns, not chaos. But then, delays. The raw readings from ESA and NASA arrived slower than expected. Official statements cited data verification protocols. Unofficially, researchers admitted they were stalling, waiting until they could explain what they were seeing. Better to say nothing than to say the wrong thing, one insider noted. That void of communication didn't last long. Into it stepped Harvard astrophysicist Avi Loeb, the same scientist who years earlier proposed that Oumuamua might be artificial. This time he came armed with a new metric, a way to score how likely an object is to be technological in origin. And 3I Atlas, he said, ranked disturbingly high. As the 3I Atlas mystery deepened, one voice rose above the noise. Harvard astrophysicist Avi Loeb, a scientist unafraid to ask uncomfortable questions. Years earlier, he'd argued that Oumuamua might have been artificial. Now he proposed a more systematic way to assess such possibilities, a technological probability scale ranging from 0 to 10. 0 means purely natural, 10 means engineered. By Loeb's calculations, 3I Atlas scored around 4. Not a verdict, but a warning. 8 distinct anomalies earned it that position: its hyperbolic path, its near-perfect orbital alignment, its reverse jet, hollow mass readings, alloy-like composition, rhythmic pulses, non-random brightness shifts, and its velocity drop near the Sun. Each one alone could be coincidence. Together they formed a pattern that probability refused to ignore. Loeb's message wasn't aliens, it was logic. The question isn't who built it, he said, but how such behavior exists without breaking physics. His stance is deceptively simple. If something looks engineered, test it as if it were, until proven otherwise. It's a discipline of radical empiricism that both fascinates and unsettles his peers. Michio Kaku weighed in with cautious respect. Curiosity is the first step in science, he said, but patience is the second. Kaku sees Loeb's work not as provocation, but as an essential exercise in humility. The cosmos, after all, doesn't care about our comfort zones. We need courage to ask the unaskable and restraint not to answer too soon. Inside observatories, Loeb's challenge ignited a quiet revolution. Researchers began testing models for hollow interiors, exotic reflectivity, even structural lattices that could channel solar radiation. None fully matched observations, yet all pointed to one conclusion: 3I Atlas was behaving like something organized. Loeb argued that denying this line of inquiry would itself be unscientific. We can't reject the simplest explanation just because it feels extraordinary, he wrote. The uncomfortable truth was that extraordinary was quickly becoming the new ordinary. 3I Atlas had forced astrophysics to look in a mirror, and the reflection was no longer purely natural. Then came fresh data from spin analysis. The rotation rate was too slow for its estimated size. Inertia and structure didn't align. Once again, the numbers whispered the same refrain: hollow, lightweight, deliberate. It was the final clue before the investigation, turned inward, literally. The spin data of 3I Atlas presented a paradox. It rotated too slowly for its size, yet remained remarkably stable. According to classical mechanics, a body that large should either spin faster or wobble apart. But 3I Atlas did neither. It moved with serene balance, the kind that suggests not mass but design. Computer models tried to simulate the effect using different densities and shapes. None matched the real observations. The only configuration that worked was a hollow shell, an object with mass concentrated on the surface and almost nothing inside. Mathematically, it was the equivalent of a 5-kilometer bubble made of something impossibly strong. Torque readings confirmed the anomaly. The moment of inertia didn't fit a solid body. Something inside dampened motion without breaking cohesion, the way engineered shock absorbers would stabilize a spacecraft. For geologists, that's absurd. For aerospace engineers, it's familiar. The data seemed to blur the line between accident and architecture. Some scientists saw a natural explanation, maybe a fragile lattice of ice and dust, a cosmic sponge of voids and tunnels. Others pointed to structure, a heat-resistant shell, perhaps hollow by design, capable of surviving near the sun. Either way, it wasn't behaving like a simple rock. It was behaving like a system. Michio Kaku has said that nature builds what works. If a hollow body endures solar stress better than a solid one, maybe evolution, cosmic or technological, found that solution long before we did. It might be a natural survivor, or it could be a relic, an ancient construct, preserved by time and cold, continuing a journey started long before humanity's first spark. Space agencies, now fully aware of the implications, began to probe further. Radar imaging, thermal mapping, and deep spectral analysis were all aimed at testing one question. Does the heat disperse evenly, or does it reveal cavities within? The answer could expose the object's true nature, or conceal it forever. Meanwhile, amateur astronomers noticed something uncanny. Around 3I Atlas, faint glimmers of light appeared, drifting, separating, then rejoining in rhythm. Dust, debris, or perhaps smaller companions following formation. To the untrained eye, they were just reflections. To scientists, they looked like choreography. With 3I Atlas once again visible and its internal mystery deepening, the world's astronomers entered a phase of watchful silence. Every major observatory from Chile to Hawaii pointed its sensors toward the interstellar visitor. The goal was no longer just to observe, but to anticipate. What would it do next? For the first time, a truly global campaign of cooperation unfolded. NASA, ESA, and JAXA synchronized tracking schedules, merging optical, infrared, and radio data in near real time. Even amateur astronomers joined the grid, providing supplemental footage from backyard telescopes. Humanity, united by curiosity, formed a planetary surveillance network, not of fear, but of fascination. The expectation was clear: the comet should begin to break apart. Natural bodies that endure solar stress tend to fracture, losing mass and brightness as they move away from the sun. But 3I Atlas refused to fade. It remained intact, stable, and then, astonishingly, began to show multiple points of light around it, each moving in a coordinated pattern. Were they fragments, or something more organized? The points drifted outward at steady intervals, maintaining symmetrical distances, a choreography that defied randomness. Statistically, this kind of dispersal shouldn't happen by chance. To some, it looked like shedding debris. To others, it resembled deployment. Michio Kaku once mused about the messengers of the cosmos, objects that might scatter across space not as accidents, but as couriers. Perhaps the universe communicates through motion, he said. We just haven't learned its language yet. Those words echoed now as astronomers watched the lights expand, like seeds carried by solar wind. Public excitement soared. Amateur footage flooded social media, showing the traveler and its mysterious companions. Some clips were verified, others dismissed, but one fact remained. 3i Atlas was no longer alone. Official agencies, cautious as ever, withheld comment. Silence, once again, became strategy. And so, the waiting began. The object continued its slow, deliberate glide across the sky, as if deciding its next step. Every shift in brightness, every flicker, every pulse mattered. Because this time, humanity wasn't just observing motion, it was witnessing intention, or the closest thing nature has ever shown to it. As new data continues to trickle in, one pattern stands out. The deeper scientists look into 3i Atlas, the quieter the institutions become. Not the silence of secrecy, but the silence of uncertainty. Michio Kaku calls this the zone of cognitive discomfort, where discoveries grow so extraordinary that language itself hesitates. That hesitation now defines the conversation around this object. Press releases have become cautious, phrases carefully chosen, under review, data pending, further confirmation required. Agencies aren't denying anomalies, they're just refusing to interpret them. It's the kind of silence that says everything without saying a word. A pause, not from fear, but from respect for the unknown. Behind the scenes, that pause is anything but idle. Laboratories are testing new models of thermal behavior. Engineers are running simulations on structural resonance. Philosophers of science are asking whether humanity has finally encountered what they call an epistemic limit, the boundary between what can be measured and what can only be imagined. Kaku reminds us that every great discovery begins with discomfort. When something doesn't fit, he says, it's the universe telling us our story is too small. That discomfort is not failure, it's evolution. Perhaps 3i Atlas isn't just challenging our physics, but our confidence in understanding the cosmos at all. Beyond the numbers, something deeper lingers. This isn't just a scientific anomaly, it's a mirror held up to our species. Maybe the universe isn't an empty stage, but a dialogue we've only just begun to hear. The silence between those lines could be the cosmos waiting for us to respond. Perhaps this visitor never came for us, but merely passed us, a drifting message written in gravity and light. A reminder that discovery isn't always an act of seeing, but of finally noticing what's been there all along. And in that realization, 3i Atlas has already succeeded. It's reignited wonder. As Kaku often says, awe is the engine of civilization. Whether natural or crafted, this traveler has pushed humanity one step beyond comfort, into curiosity, and its silence, vast and eloquent, whispers a single truth: the story of the universe isn't finished yet.